Hello, welcome again to Tricky Calculations with Dr. John. I'm Dr. John, and this is episode 2 of Tricky Calculations, where we will be looking at bond enthalpy. So here is the question. Propane undergoes complete combustion. We're given the equation of the reaction, and we're given the enthalpy change of the reaction as negative 2046 kilojoules per mole. We're given a table that shows some bond enthalpy data. We are given the equation that occurs when water vaporizes from liquid to gas, and we're told that the enthalpy is positive 41 kilojoules per mole. We are asked to calculate the carbon-carbon bond enthalpy in propane, and this question is for 4 marks. Why is this question tricky? Well, the very first one is that students often miscount the number of bonds, especially carbon-carbon single bonds. Now, when we solve bond enthalpy questions, I like to have students draw out in displayed formula the molecules that are reacting. So if we look carefully, we'll see that we have a molecule of propane drawn out in displayed formula with all the bonds shown, reacting with 5 moles of oxygen, drawn out again in displayed with the bonds shown, to give 3 moles of carbon dioxide or carbon 4 oxide, again drawn out and displayed, plus 4 moles of water. The reason why I like students to draw this out and display this because it becomes very easy for you to count up the number of bonds. Okay, now we can very quickly look at the bonds that have been broken, and that's by counting up the number of bonds. So you can see that we have 2 carbon-carbon single bonds, we have 8 carbon-hydrogen single bonds, and we have 5 oxygen-oxygen double bonds. So if we write this out, then we can very quickly calculate out the value of the energy required to break those bonds. Now, we don't know what the value of the carbon-carbon bond is, so we will leave it as it is. And then we will do 8 times 412 plus, again in brackets, plus 5 times 496. If we sum that up, we will get 3296 plus 2480, and when we add that up, we will have 2 times carbon-carbon single bond plus 5776. I've taken the time to do this separately, and then we are going to do the bonds made separately, and then we're going to add them together. Now, the second thing that makes this problem quite tricky is that bond enthalpy is measured in the gaseous state, not in the liquid state. So bond enthalpy is the energy that is required to break the bonds in the gaseous state, to break 1 mole of the bonds in the gaseous state. So this is very important because the original equation that we've been given gives us 4 moles of water in the liquid state. So we must first convert those 4 moles of water to the gaseous state before we break the bonds. So if we look at bonds made here, we can again write out the number of bonds that have been made. We see that for our carbon dioxide, we have 3 moles of carbon dioxide. Each one is made up of 2 carbon-oxygen double bonds. So that's why we have 3 times 2 times C double bond O. Then in water, we have 4 moles of water. Each mole of water has 2 oxygen-hydrogen bonds. This is why we have 4 times 2 times the oxygen-hydrogen bond. And very importantly, and I've marked this in red, we adjust for the enthalpy required to convert the liquid water to gaseous. This is why we add 4 times 41. So the 41 is to convert each mole of liquid water into gaseous water. 4 times 41 is because we have 4 moles of liquid water there. Okay, so if we add up everything, we'll get 6 times 743 if we multiply, then 8 times 463 plus 164, and if we add that up, we will get 8,326. That is the value for bonds made. Very importantly, we then have to deal with combining these enthalpies, and what tends to happen here is that students tend to make a mistake with managing the positive and the negative enthalpies. First, we state the equation that we need. The enthalpy change of reaction will be given by the summation of all the bonds that have been broken plus the summation of all the bonds that have been made. This is why I've calculated it out separately so that we can just substitute directly into this equation. The key thing to note is that bond breaking is exothermic. So if we have a bond and we want to break that bond, then we will need to put some energy to split that bond. So bond making is inherently endothermic. And on the other hand, bond making is exothermic. So if we make a bond, we release energy. Therefore, the enthalpy change of reaction will be negative. This means that the bond's broken side, 2 times Cc plus 5776, will come with a positive, and the bond's made side which is 8326, will come with a negative sign. Okay, let's put that together and then we calculate. So the enthalpy change of reaction, negative 2046, is equal to 2 times the carbon-carbon single bond plus 5776, all of that is positive, plus minus 8326. Again, the minus sign is because bond making is exothermic and therefore the enthalpy must be negative. If we put this together and we simplify, we will then have negative 2046 is equal to 2 times Cc minus 2550. If we collect like terms together, we will have negative 2046 plus 2550 will give us 2 times the carbon-carbon single bond, and then we will get positive 504 is equal to 2 times the carbon-carbon single bond. Now, many students end here, and that is another reason that this question is tricky. You need to divide your answer by 2. So remember, we're looking for the value of the carbon-carbon single bond. So if we divide our answer by 2, we will get our answer as positive 252 kilojoules per mole. All right, now let's look at how this question is marked. Remember that it is 4 marks. The very first mark is given for your ability to calculate the bonds broken and the bonds made. Okay, you need both of them to score the first mark. The second mark is obtained by showing the adjustment for your liquid water becoming gaseous. So if you show 4 times 41 at any point, you will get M2. Next, for M3, once we have calculated positive 504 as being equal to 2 times the enthalpy change of the carbon-carbon single bond, that will be M3, and then M4 is obtained when you divide by 2. Okay, now I know that this question has been a bit tricky and we've solved it. I want you to go back, watch this again, try your hand at solving the problem and see how you do. Remember, please keep in contact because there are even more tricky calculations that are going to be coming as part of this series. Thank you so much for joining, and I will catch you on the next one. Cheers.